So hello and welcome in this video on two-dimensional continuous random variable. Okay, so basically we are discussing about the two-dimensional continuous random variables. So let us assume that we are having two continuous random variable, let's say x and y. So these x and y are two continuous random variables which are defined over the same sample space. Okay, so we have a function of which is defined in terms of these two random variables x and y, which is known as the joint probability density function. Okay, this is joint probability density function. So this function, which is defined in terms of the random variables x and y, has needs to satisfy certain properties. In fact, two properties. So the first property is that the value of this function over the domain is always greater than equals to 0, or you can say it will take non-negative values over the entire domain of definition. The second property is that when you integrate it with respect to x and y, means when you perform the double integration of this function, so this is equals to 1. The value of this double integral is 1. Now the very important concept is the limits of this double integral. So because in general we assume that both the random variables are defined from minus infinity to plus infinity. So in general we consider the limits as minus infinity to plus infinity, but yes, we need to modify these limits as per the definition of the function fxy. So this property is very helpful to determine the any unknown involved in the expression of our fxy. So we can determine the unknown. Okay, we can determine the unknown involved in fxy, right? So we can determine the unknown. Now let us discuss some basic problem on this two-dimensional continuous random variable. So our problem number 1 is, we are given that this function, which is defined as k times xy, is the joint PDF. Okay, and the domain is also given to us that x and y both varies from 1 to 2. So this function is the joint PDF. Okay, now we have to find out the value of the unknown, means the value of k. What is the value of this unknown? So let us begin with the solution. So as I mentioned here, that in general we consider the limits as from minus infinity to plus infinity, but we have to modify the limits as per the definition. So here you can see that the limits for x and y you can obtain from here, and both varies from 1 to 2. So we use this second property. So because it is given to us that it is the joint PDF, so we can directly use this second property, and the limits will be same for both the variables, that is 1 to 2. Now we have to integrate our fxy, which is k times xy. Out of these three terms, k is constant, so you can take it out from the integral, and we are having dx dy. Now when you, because you are performing first the integral with respect to x, so you can keep y as it is, and when you integrate the x with respect to x, so you will get x square by 2. Now the limits are 1 to 2, and because we have yet to integrate with respect to y, so the limit for y will remain as it is, and here we are having dy. Now when you integrate, and yes, the value of this integration is 1 because we are using this property. Okay, you can also write it that this is 1. So from here you will obtain k times 1 to 2 y, and when you are putting the limits, so when you put x is equals to 2, so it is 4 divided by 2 is 2, minus when you put x is equals to 1, so this is 1 by 2, and we have yet to perform the integration with respect to y. Now we know that this 2 minus half is 3 by 2, and again 3 by 2 is constant. Okay, so the value of this is 3 by 2. Okay, so we will, because this is constant, so we can take this outside from this integral. So from here you will obtain 3 by 2k, and the limits are 1 to 2, and we have to perform the integration with respect to y. So this will give us 3 by 2k, and of course this is equals to 1. So when you perform the integration of y with respect to y, so we will obtain y square by 2, and our limits are 1 to 2, and we have to put this integral equal to 1. So from here you will obtain 3 by 2k, and again if you are putting the limits here, so this is 2 minus 1 by 2, and this is equals to 1. So again from here you will obtain that this value is again coming out as 3 by 2. So we are having 3 by 2 here and 3 by 2 again, so this will be 9 by 4, k is equals to 1. So this gives us the value of k as 4 by 9. So this is how we can obtain the unknown involved in the expression of our joint PDF. Now it is very important that whenever you are dealing with the two-dimensional continuous random variable, because every time we need to perform this double integral, so it is very strongly recommended that you have a clear understanding of this multiple integral, in particular the double integral, because if you are not having the concept of this double integral, then you cannot deal with the problems on two-dimensional continuous random variable. So we are taking another example. So here again we are provided this joint PDF. So I am taking this expression of the joint PDF as it is, but this time what I do, I just take the limits and I am changing the domain of definition for this function. In the previous, or in the example number 1, it is x comma y both varies from 1 to 2, but now you can see that again we are having x and y are lying between 1 and 2, but apart from this we are having another condition with that is this y should always be greater than x. So this is the case when we are not having the constant limits, right? So first of all we will just need to sketch the domain over which our fxy is defined. So first we are putting this x, so we are focusing on x, and now if you are looking at x, so x is varies from 1 to 2, so we are putting x is equals to 1. Okay, so this is our x is equals to 1, and we are drawing this another line which is x is equals to 2. Similarly we are having y is equals to 1. Okay, so this is y is equals to 1, and we are having this y is equals to 2. Now just look at this limit which states that we are having y always greater than x. So in order to determine this region what we will do, we just plot a line which is very common, and that is y is equals to x. So y is equals to x is a line passing through the origin. So we are plotting this. So here we have we will use the idea of equation of line or the sketch of line passing through the 2 points. So we need to find out 2 points. So for this line, first point is this origin, which is 0 cross 0, because here you can see that y and x both are 0, so they are equal. Now this point of intersection of x is equals to 1 and y is equals to 1, so the coordinate of this is 1 comma 1, and the point of intersection of x is equals to 2 and y is equals to 2, so this is 2 comma 2. Now this line y is equals to x will passes through this these points, and because it is given that x and y both lies between 1 and 2, so we don't need to extend this towards or in this third quadrant. Now if you look at this, this is our domain. Okay, this is our domain over which our function is defined. So this is our domain. Now what we have to do, we have to obtain the limit. So in order to obtain the limit, we have plotted this domain. So you can see that this line y is equals to x is dividing this domain of this function into 2 parts. Okay, so I am calling this part as A and the second part as B. So because the condition is x is less than equals to y, and we know that on this line, which is y is equals to x, x and y both are same. So now this line divides this domain into 2 parts, A and B. So our part A is our required part. Okay, means in part A, you can just mention that in part A we are having y as greater than equals to x, while in part B we are having x is greater than equals to y. So here we are having this upper triangular region. So first we have to perform the double integral. Okay, we need to perform the double integral, and we have to find out the value of the unknown. Unknown is this. Okay, so we are just performing the integral. So again I am taking this k outside because it is constant, and I am performing the integral with respect to x and y. Now the very important thing is what will be the limits, and in order to get the correct limits, we need to identify the region or domain over which we have to perform the double integral, and as we determine that this is our required region. Okay, because we are given that x is less than equals to y. So now if you are taking this upper or just vertical strip, so you can see that this strip is begin at this point which lies on y is equals to x. So the lower limit of this double integral is x, and this strip ends here, which is y is equals to 2. So we are having y is equals to 2, so the upper limit is y is equals to 2. Now we are having another important limit, and that is for x. So when you are moving in this domain, okay, when you are moving in this domain, so this x will varies from 1 to 2. Okay, this is 1 to 2 because you can see that this from this point this line is x is equals to 1. Okay, this line is x is equals to 1. So x will starts from here and move up to this point where x is 2. So the limit for x are 1 to 2. Now we have to perform the integral. So first we are performing the integral with respect to y. So we are taking x as it is, and when you are performing the integral, so it is coming out y square by 2, and we have yet to perform the integration with respect to x. So from here you will obtain 1 to 2, and of course the limits for y are x to 2. So this will be x, and here we are having when you are putting the upper limit, which is y is equals to 2, so we will get 2 minus x square by 2 dx is equals to 1. So this gives us that k times 1 to 2, and this will be 2x minus x cube by 2, and we have to perform the integral with respect to x, and we know that the value is coming out as 1. So from here you will obtain the value, means when you are performing the integral, so integral of x is x square by 2. So this is x square minus, we are having x to the power 4 over 8, and we are having the limits as 1 to 2. So from here when you are evaluating the limits, so first we have to find out the value of this expression on the upper limits, which is x is equals to 2. So we are having 4 minus, when you are putting x is equals to 2 here, so this is 2 to the power 4, which is 16. So this is 4 minus 2. So this is the value of our expression at x is equals to 2, minus we have to subtract the value of this expression at the lower limit, which is 1. So this is 1 minus 1 by 8, and this is equals to 1. So from here you will obtain that this is coming out 4 minus 2 is 2, minus, and 1 minus 1 by 8 is 7 by 8. So this is 7 by 8 is equals to 1, and that will again give you the value, and that is 4 minus this is coming out as 9 by 8 k is equals to 1, or you can say that k is coming out 8 by 9. So this is how we can use our property number 2 of this joint PDF in order to determine the unknown involved in our definition. Now in two-dimensional continuous random variable, similar to the case of discrete random variable, we have the concept of marginal density function. Okay, we have the concept of marginal, and we are also having the concept of conditional. So how we can find out the marginal and conditional density function for two continuous random variables? So let's say we are given fxy, which is our joint PDF. Okay, this is our joint PDF. Now in order to get the marginal, okay, so in order to get the marginal for x, what we will do, we will integrate our joint PDF fxy. Now we are looking for the marginal for x, so we have to perform this integral with respect to y, because we are looking for the marginal of x. And again, because we are not having any particular expression, in place of that we are dealing with a general expression, so we are keeping the limits as minus infinity to plus infinity, but you can determine the limits can be determined from the limits can be determined, okay, can be determined, limits can be determined from the definition of fxy. Okay, so we use the definition of fxy and we use the domain. Okay, so let us discuss the marginal. Okay, so let us discuss the marginal for the second or the other random variable, which is y. So that is the function of y alone, and we can obtain this from the joint PDF again by performing the integral of this fxy, but this time with respect to x. Okay, and yes, we can determine the limits. So this remark is still here, that we have to determine the limits as per the definition of our joint PDF. Okay, so we have to look at this definition, and we obtained the limits from the definition itself. So this is how we can find out the marginals for x and y. Now once we are having the marginal, we can easily find out the conditional density function. So the conditional, or you can say f of x given y or f of y given x. So we can find out the values of or expression of these two conditional density function. So f of x given y means the conditional density function of x given y. So we can simply obtain this from fxy divided by fy. Okay, so here this fy is the marginal. So this is marginal of y, while this is our joint PDF. So we have to divide our joint PDF by the marginal of y, and we will obtain this conditional density function. Similarly, we can obtain the conditional density function of y given x, and here we again divide this fxy, means the joint PDF, but this time by x, which is the marginal of x itself, right? So this is how we can obtain the marginal and conditional density function. So here let us discuss this calculation or the expression of our these density functions. So we continue with our previous problem, which is so here you can see that we are provided with this joint PDF together with this definition of, or the definition of the domain of fxy. So we are given this fxy as k times xy, and this domain is given as x and y both varies from 1 to 2. So we are having fxy as kxy, and we are having that this x and y both varies from 1 to 2, but this time with a condition or restriction that y is always greater than equals to x. So again let us make a diagram here so that we can clearly understand the use of limits. So we are given the domain as x and y both varies from 1 to 2. Okay, so we are having this x is equals to 1, x is equals to 2. Now we are having this y is equals to 1 and y is equals to 2. So these this is our domain. This triangular region is our domain. Now just like the previous problem, again we draw a line which is y is equals to x. So we have to draw this because that will give us the exact domain. So when you plot this line, so this will be passing through these points, because this point is the intersection of x is equals to 1 and y is equals to 1. So this is 1 comma 1, and similarly this point is 2 comma 2. Now we are given this restriction where y is always greater than equals to x. So because we are having two triangular regions which is given by this line, which is y is equals to this line is y is equals to x. So this is given to us. So this is the region, as we already discussed. This is the upper triangular region, is the region where we are having y is greater than equals to x. So let us find out the marginal for the variable x. Okay, so we have already obtained the value of this constant, means k here. So this value of k is coming out as 8/9. So our fxy, after putting the value of k as 8/9, will be 8/9 xy. Now marginal for x, in order to derive this marginal, we have to integrate our xy with respect to y, and here we have to put the limits as per our variable y. So the value of k is, which we obtained, is 8/9, and the function is xy. Now we are performing the integration with respect to y, so we are taking the vertical strip, right? So you can see that this strip starts from this line y is equals to x. So the lower limit for this integral is x, and this strip ends at y is equals to 2, so the upper limit is 2. Okay, now when you perform this integration, so we have to perform only one integration here, because we are not having dx dy. Here we are having only dy, means we have to perform the integration with respect to y only. So we can take this x outside, and this is y square by 2, and the limits are x to 2. So when you are putting the upper limit, okay, so we are giving 8/9 x. Now when you are putting y is equals to 2, so we are given 4 upon 2, which is 2, minus we will have x square by 2, means which is the value, or value of this expression, which is y square by 2 at x. So this will give us 8 by if you take this 2 as LCM, so that will give you this as 8/18x, and here you will have 4 minus x square, or you can simplify this. So this will be 4/9x, 4 minus x square. So this is our marginal for x. Similarly, we can obtain the marginal for y. So in order to obtain the marginal for y, we have to integrate our function, which is 8/9xy, with respect to x. Now when you are performing this integral, you have to consider the horizontal strip here. So let us first make this marginal for y. So we represent this by fy, and we have to integrate our joint PDF. Now this integral is with respect to x, right? And now we are putting, because this is the general definition, so we are putting the general limits. Now once you are putting the value or expression of fxy, okay, so this is k times xy, and when you are putting the value of k here, so this is coming out 8/9 xy. So we will integrate this fxy, which is 8 by 9 xy, and we are performing this integral with respect to x. So due to this, we have to consider our strip which is parallel to our horizontal axis, or you can say the x-axis. So this strip starts from this line, okay, which is our x is equals to 1, and this strip ends at this line, okay, which is y is equals to x. So our limits are, as per this horizontal strip, is 1 to 1 to, and in place of y I am writing here x. Okay, so because we are looking for the limits for the variable x, so sorry, this is not x, here we have to put, because we are looking for the limits of x, so we are putting here y, because this strip ends at this line which is y is equals to x. So we are getting 8 by 9, and once you are because we are performing the integration with respect to x, you can take this y outside, and here we are having x square by 2, and limits are 1 to y. So this will be 8 by 9 y, and when you are putting the limits, so that will be y square by 2 minus 1 by 2. So that will be 4 by 9 y square minus 1. So this is our marginal for y. Now suppose we have to find out the conditional density function. Okay, so we are having two conditional density functions. First, for x given y, so that will be fxy divided by fy. So our fxy is 8 by 9 xy, and this fy is you can see that this is 4 by 9 y. So this is 4 by 9 y square minus 1. So this is our fy. So this will, on simplification, you will get 2x over y square minus 1. So this is our conditional density function for x given y. Similarly, we can obtain the expression for conditional for y given x. So we can write this as f of y given x, and that will be fxy, which is our joint PDF, and we have to divide this by fx, and this fx is the marginal for x, which we already obtained here. So that is 4 by 9 x 4 minus x square, and fxy is 8 by 9 xy, and here in the denominator we are having the fx. So fx is here, which is 4 by 9 x 4 minus x square. So this is 4 by 9 x 4 minus x square. Okay, so this is our fx. Let me check. So this is yes, so this is 4 by 9 x 4 minus x square. So first of all, we cancel out this x, and we also cancel out this 9, and we cancel this 2 times. So this is coming out as 2y over 4 minus x square, and this is our conditional density function for y given x. Okay, So this is how we can obtain the marginals, conditionals, and the value of the unknown involved in our joint PDF. And in our next lecture we will discuss about the probability, means how we can calculate the probabilities for two-dimensional continuous random variable and some more concepts. So that's all. Thank you.